November 19th, 1942. A testing ground outside Kummersdorf, Germany. Wehrmacht ordnance engineers gathered around a peculiar tube captured weeks earlier in Tunisia. 1 meter and 38 centimeters of simple steel pipe. No recoil mechanism, no complex breech assembly. Just a hollow cylinder with rudimentary sights and a grip assembly housing a battery contact. The Americans called it a bazooka.
If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today.
Oberst Heinrich Fichtner of Prüf 6 studied the device with professional skepticism. For decades, anti-tank doctrine had been clear. You needed either a high-velocity gun mounted on a heavy carriage or a tank destroyer with enough armor to survive counterfire. The physics were immutable. To penetrate 100 millimeters of hardened steel, you needed either kinetic energy delivered by a massive projectile traveling at tremendous velocity, or you needed to get close enough to place explosive charges by hand. Both options meant either tonnage or death. There was no third way. The captured American rocket projectile lay beside the launcher, the M6 warhead, 60 millimeters in diameter, 1.53 kilograms total weight. Inside the nose cone, a copper-lined conical cavity filled with approximately 720 grams of high explosive. The engineers had already dissected several captured specimens. The shaped charge principle was known to German scientists. The Monroe effect, the focused jet of superheated gases and molten metal capable of cutting through armor plate like a blowtorch through butter. But shaped charges were heavy. The experimental German weapons using this principle required deployment by squads. They were rifle grenades too unwieldy for practical use, or towed launchers that sacrificed mobility for firepower. This American tube changed the equation. Solid propellant rocket motor, electrical ignition, shoulder fired by a single infantryman. The testing parameters were straightforward. Fire the captured rockets at rolled homogeneous armor plates of varying thickness. Measure penetration. Assess reliability. Determine if this curious weapon represented a genuine threat to German armor, or merely another example of American mechanical novelty divorced from battlefield reality. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The first shot was fired at 1400 hours. The rocket motor ignited with a sharp crack. White smoke billowed from both ends of the tube. The projectile wobbled slightly in flight, 80 meters per second. Painfully slow by artillery standards. The warhead struck a 50 millimeter test plate at 30 degrees obliquity. The shaped charge detonated. When the smoke cleared, the engineers found a hole punched cleanly through the steel. Penetration complete. The observers exchanged glances. 50 millimeters was enough to defeat most armored vehicles' side protection. The second test used an 80 millimeter plate. This represented the side armor of a Panzer IV medium tank. The American rocket penetrated again. The third shot targeted 100 millimeters, the frontal armor thickness of many German medium tanks. The warhead punched through. At 120 millimeters, penetration became inconsistent. Some shots achieved breakthrough, others failed. But the implications were already clear. A 14-pound tube carried by infantry could defeat armor that previously required dedicated anti-tank guns weighing hundreds of kilograms. Fichtner requested immediate analysis. The weapon's vulnerabilities were obvious. The battery ignition system proved unreliable in cold weather. The pointed nose of the M6 rocket deflected off sloped armor at shallow angles. The effective range was limited to perhaps 100 meters, maybe 150, in ideal conditions. Beyond that, the slow rocket velocity and crude sights made accurate fire impossible. The backblast signature revealed the firer's position immediately. A single shot would draw concentrated enemy fire. The thin launch tube offered no protection to the operator, but the fundamental principle remained sound. The Germans possessed rockets. The Wehrmacht already fielded the 8.8 centimeter Raketenwerfer 43, a crew-served rocket launcher designed to engage armor. Its warhead, the RPZB.GR.4312, used an 88 millimeter shaped charge, the same diameter as the legendary 88 millimeter anti-aircraft gun that had earned fearsome reputation as an improvised anti-tank weapon. If the Americans could miniaturize a rocket launcher for one-man operation, so could Germany. And if the Germans scaled up the warhead from 60 millimeters to 88 millimeters, penetration would increase dramatically. The ordnance staff began calculations immediately. An 88mm shaped charge could theoretically penetrate 160mm of armor at 100 meters. That would defeat every Allied tank in production. Sherman, Churchill, even the Soviet 34 with its sloped armor would be vulnerable from the sides and rear. More importantly, it could be produced quickly. The Raketen-Werfer 43's rocket motor could be adapted. The launch tube could be fabricated from simple steel pipe, no complex machining, no precision tooling. Just a tube with an electrical firing mechanism and basic sights. In an industrial economy increasingly strained by Allied bombing and Eastern Front demands, simplicity was strategic necessity. By early 1943, German engineers completed their derivative design, the Raketen-Panzerbuchse 43, rocket anti-armor rifle. The troops would nickname it Panzerschreck, tank terror. The weapon measured 164 centimeters in length, weighed 9.25 kilograms, empty. The 88mm rocket added 3.2 kilograms, heavier than the American Bazooka, but still man-portable. The critical modification involved the propellant. American rockets burned completely within the launch tube. German rockets, using different propellant chemistry, continued burning for approximately 2 meters after leaving the muzzle. This created an unpleasant problem. The operator stood directly behind a blowtorch. Testing crews reported burns to exposed skin. One early operator suffered temporary blindness from burning propellant fragments. The solution was crude but effective. Operators were issued protective ponchos, heavy gloves, and gas masks with the filters removed. The ensemble was cumbersome, especially in combat, but it allowed the weapon to function. A German military report dated September 9, 1943, announced the Panzerschreck would be issued to Eastern Front units immediately. Production began at Hassag Works in Muselwitz. The first units reached frontline troops in October 1943. Within months, improved models appeared. The RPZB-54 featured a blast shield to protect the operator, increasing weight to 11 kilograms, but eliminating the need for full protective gear. The RPZB-54-1 followed with a shorter barrel and improved rocket, extending range to 180 meters. But to understand why Wehrmacht engineers reacted with such urgency to the captured bazooka, we must understand what they were facing in November 1942. The context that made a simple tube appear revolutionary rather than merely interesting. The strategic nightmare that was unfolding across multiple fronts simultaneously. The armor crisis that would define German defensive operations for the remainder of the war. In June 1942, Germany still appeared ascendant. Rommel's Afrika Korps threatened Egypt. Army Group South drove towards Stalingrad. The submarine war in the Atlantic was bleeding, Allied shipping faster than it could be replaced. Panzer divisions equipped with Panzer III and Panzer IV tanks had proven adequate against British cruiser tanks and American Stuarts. The Wehrmacht's anti-tank doctrine, built around towed anti-tank guns and dedicated tank destroyers, seemed sufficient for the mobile warfare that had characterized German victories from Poland to France to the initial phases of Barbarossa. But cracks were appearing. In North Africa, American M4 Sherman tanks arrived in substantial numbers. The Sherman's 75mm gun could penetrate German medium tanks from reasonable combat ranges. More troubling was the Sherman's production rate. Intelligence reports indicated American factories were building thousands per month. Thousands. German tank production in 1942 totaled approximately 5,600 vehicles of all types. The Americans were building that many Shermans every few months, while simultaneously producing tank destroyers, light tanks, and self-propelled guns. The industrial arithmetic was becoming impossible to ignore. On the Eastern Front, the situation was worse. Soviet 34 medium tanks and KV heavy tanks appeared in numbers that dwarfed German tank production. The 34's combination of sloped armor, wide tracks for mobility, and 76.2mm gun made it arguably the best medium tank design of the war. German Panzer IV tanks could engage 34s, effectively only with improved long-barreled guns and only at favorable ranges and angles. The KV heavy tanks were nearly impervious to standard German anti-tank weapons from the front. German forces encountered KV tanks that had absorbed dozens of anti-tank gun hits without disabling damage. The Wehrmacht's response to the armor crisis followed traditional German engineering philosophy. Build heavier tanks, build bigger anti-tank guns. The Tiger heavy tank entered production in August 1942. 57 tons, 100 mm frontal armor. The fearsome 88 mm KWK-36 gun, capable of destroying any Allied tank at ranges exceeding 2 kilometers. The Tiger represented the apex of German armored warfare doctrine, technological superiority through engineering excellence. A single Tiger crew could dominate a battlefield, destroying dozens of enemy tanks before withdrawal or destruction. But the Tiger came with crippling disadvantages: mechanically complex, expensive to produce, resource-intensive. Each Tiger required over 300,000 man-hours of labor, used rare materials including nickel and molybdenum for armor plate, required precision machining for the transmission, final drives, and interleaved suspension system. By the end of 1943, Germany had produced approximately 650 Tigers. The Soviets had built over 22,000 34s. The Americans had built over 21,000 Shermans. The British added thousands more tanks of various types. For every Tiger prowling European battlefields, there were perhaps 50 or 60 Allied tanks it needed to destroy just to maintain the tactical equilibrium. This was the strategic context Wehrmacht engineers understood in November 1942 when they tested the captured Bazooka. The realization that Germany could not win a war of industrial attrition, could not produce enough heavy tanks to counter Allied numerical superiority, could not manufacture sufficient towed anti-tank guns to defend every village, crossroads, and river crossing that would need defending as the Wehrmacht transitioned from offensive to defensive operations. What Germany needed was a force multiplier, a way to give ordinary infantry the capability to destroy tanks without requiring scarce artillery pieces or precious armored vehicles, a weapon simple enough for mass production, cheap enough for widespread issue, effective enough to matter tactically. The American Bazooka, despite its limitations, suggested such a weapon was possible. A rifleman could carry it. A conscript could learn to fire it in hours rather than weeks. It required no advanced infrastructure to manufacture, no precision optics, no complex hydraulics, no sophisticated fire control systems, just a tube, a rocket, and basic electrical ignition. If properly refined and scaled up, such a weapon could be issued not to specialized anti-tank units, but to regular infantry companies. Every squad could have the capability to engage armored vehicles. Every hedgerow, every building, every tree line could conceal a tank killer. The psychological impact would be profound. Allied tankers would lose the confidence that came from armor superiority. They would need infantry support for every advance. They would need to clear every position before exposing their vehicles. The tempo of Allied operations would slow. German defensive positions would become exponentially more dangerous. A single infantry company, equipped with man-portable anti-tank rockets, could hold a critical position against armored assault, at least temporarily. Hours might be bought, days, in favorable terrain, and in late 1942, as the Wehrmacht transitioned from conqueror to defender, time was becoming the most precious commodity. But there was another realization, darker and more troubling. If American infantry possessed shoulder-fired weapons capable of penetrating 100 millimeters of armor, then German tanks were vulnerable in ways they had never been before. The Panzer IV's side armor was 80 millimeters. The Panzer III's was 50. Even the new Panther tank, designed with superior sloped frontal armor, had 80 millimeter side plates. The Tiger itself, despite its formidable frontal protection, carried 82 millimeters on the turret sides and 60 millimeters on the hull sides. The Bazooka didn't threaten German tanks from the front at combat ranges. Its limited range and the Tiger's thick frontal glacis plate meant head-on engagements favored the tank. But warfare wasn't a duel fought at carefully chosen ranges on open terrain. It was chaos. It was close quarters fighting in villages where tanks maneuvered slowly. It was ambushes from flanks. It was engagements at ranges measured in tens of meters, not hundreds. In those conditions, the Bazooka was lethal. A teenager in a crater with a 14-pound tube could mission kill a 57-ton Tiger by hitting the drive sprockets or engine compartment, could disable the turret traverse by striking the turret ring, could cause ammunition fires by penetrating side armor into the fighting compartment. Wehrmacht tactical analysis from late 1942 drew explicit conclusions. Tank operations would need to change. Armor could no longer advance without extensive infantry screening. Every position would need to be suppressed with artillery before tanks could safely approach. The speed of armored exploitation, The blitzkrieg doctrine that had delivered victory after victory would be constrained by the infantryman with a tube. The weapon that democratized anti-armor capability also democratized defensive capability. It gave the weak tools to hurt the strong. It made concrete what many German officers were beginning to suspect. The era of armored dominance was approaching its apex. The pendulum was swinging back toward defensive warfare where prepared positions, obstacles, and man-portable weapons could blunt armored attacks that would have been unstoppable 2 years earlier. Field Marshal Erwin Rommel, commanding forces in Tunisia when the first bazookas were captured, received intelligence reports on the new weapon immediately. Rommel understood combined arms warfare better than perhaps any German commander. He recognized that the bazooka represented not just a new weapon, but a shift in the fundamental relationship between armor and infantry. In previous campaigns, infantry without dedicated anti-tank guns were effectively helpless against tanks. They could scatter, they could hide, they could hope the tanks would pass by, but they couldn't fight back effectively. The bazooka changed that equation. Now every enemy infantry section might have tank-killing capability. Every assault would need to account for shoulder-fired rockets emerging from positions that appeared to contain only riflemen. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Rommel's tactical directives from early 1943 emphasized the vulnerability of tank sides and rear to the new American weapon. Panzer crews were instructed to maintain maximum standoff distance from enemy infantry, to use their gun range advantage to engage before closing to rocket range, to angle their hulls when static to maximize effective armor thickness, to absolutely avoid close-quarters combat in urban terrain where bazookas would have every advantage. The directives revealed professional respect for a weapon that was, objectively, limited in capability. But limitations didn't matter if you were the crew of a burning Panzer IV that had advanced too close to a hedgerow concealing enemy rocket teams. By mid-1943, German Panzerschreck production reached scale. By the end of the year, thousands had been issued to frontline units. The weapon appeared on every major front where German forces operated. In Italy, Panzerschreck teams positioned in rugged mountain terrain ambushed Allied armor advancing along predictable routes. The restrictive terrain channeled tanks into kill zones. Carefully positioned rocket teams could engage at favorable angles, targeting sides and rear as vehicles maneuvered through defiles and around obstacles. Multiple accounts from Allied tankers describe the psychological impact of knowing that any stone wall, any cluster of trees, any shell crater might conceal a Panzerschreck. The weapon forced caution, slowed advances, made every meter of ground more costly. On the Eastern Front, the Panzerschreck became a critical defensive tool. Soviet armored doctrine emphasized mass and momentum. Tank brigades would concentrate for breakthrough operations, exploiting gaps with speed and shock. German infantry, often lacking heavy anti-tank guns after the weapons had been destroyed or overrun in previous battles, relied on Panzerschrecks for last-ditch anti-armor defense. The weapon couldn't stop a Soviet armored offensive. No man-portable system could, but it could blunt attacks, could destroy lead tanks and cause following vehicles to button up, slow down, spread out, could buy hours for German forces to establish new defensive positions or conduct tactical withdrawals. In the desperate defensive battles of 1944 and 1945, those hours sometimes meant the difference between orderly withdrawal and encirclement. In Normandy, Panzerschreck teams became specialists in hedgerow warfare. The bocage terrain of northern France consisted of small fields bordered by thick hedgerows on raised earth banks. Visibility was limited to tens of meters. Tanks advancing through this terrain were vulnerable from multiple directions simultaneously. German Fallschirmjäger and Panzergrenadier units would position Panzerschreck teams in carefully chosen positions. The tactic was simple but effective. Wait until Allied tanks committed to advancing through a particular gap or along a specific route. Allow the lead tank to pass. Then engage the second or third vehicle from the flank, disabling it in the narrow passage and blocking the route for vehicles behind. The destroyed or damaged tank became an obstacle, forcing following vehicles to halt, expose flanks while maneuvering, or withdraw. Small-scale engagements delayed Allied advances by hours or days. Individual Panzerschreck teams didn't win battles, but they contributed to the grinding, costly nature of the Normandy campaign, where American and British forces measured progress in hundreds of meters rather than kilometers. Statistical analysis of the weapon's effectiveness reveals interesting patterns. German combat reports from 1944.
If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this.
Indicate that Panzerschreck teams typically needed multiple rockets to achieve a kill. First-round hit probability at 100 meters was estimated at 60 to 70%, falling to perhaps 30% at 150 meters. But hit didn't necessarily mean kill. Many hits struck at angles that caused the shaped charge to fail to penetrate. Others penetrated non-critical areas that didn't disable the vehicle or harm the crew. Tank designs evolved to counter shaped charge weapons. Allied tanks began appearing with improvised additional armor. Sandbags packed along the sides, spare track links welded to hull plates, wooden logs strapped to turret sides. None of these measures were particularly effective, as tests later demonstrated the shaped charge needed approximately 1 meter of standoff to significantly reduce its penetrating effect, and sandbags or track links provided nowhere near that distance. But the very presence of improvised armor indicated that Allied tankers took the Panzerschreck threat seriously enough to burden their vehicles with extra weight that degraded mobility and mechanical reliability. The German military produced approximately 314,895 Panzerschrecks of all variants during the war. This number pales beside the millions of rifles or hundreds of thousands of machine guns manufactured. But it represented a substantial investment for a weapon that hadn't existed before November 1942. More importantly, the concept proliferated. The Panzerfaust, a simpler disposable rocket launcher, entered production in mid-1943. By war's end, nearly 7 million Panzerfäuste had been manufactured. The combination of Panzerschreck and Panzerfaust gave German infantry anti-armor capabilities that simply didn't exist in 1941. They didn't make German forces capable of defeating Allied armored superiority. The industrial and numerical balance was too far tilted. But they made German defensive positions significantly more dangerous and costly to reduce. Allied commanders adapted. Tank-infantry cooperation became mandatory doctrine. Infantry would clear potential rocket positions before armor would advance. Artillery would saturate suspected Panzerschreck locations with high explosive fire. Allied air superiority meant that German anti-tank teams faced strafing attacks from fighter bombers equipped with rockets and bombs. The tactical environment became a deadly competition between German defensive tactics and Allied combined arms responses. Neither side achieved dominance. Instead, both sides adapted continuously, producing the grinding attritional warfare that characterized the Western European campaign from Normandy to the Rhine. Soviet forces dealt with the Panzerschreck differently. Soviet armored doctrine accepted high casualties as the cost of maintaining offensive momentum. Tank crews were considered expendable. Vehicles were expected to be destroyed. What mattered was whether the objective was taken. If a tank brigade of 100 vehicles took an objective while losing 40 tanks to various causes, including Panzerschreck attacks, Soviet commanders considered this an acceptable exchange. The brutal calculus reflected Soviet industrial capacity and demographic resources. The Soviets could replace destroyed tanks faster than the Germans could replace Panzerschreck operators. The mathematics of attrition favored the side that could absorb losses and continue attacking. German forces found that Panzerschrecks could destroy individual Soviet tanks but couldn't stop Soviet offensives. The weapon provided tactical successes without strategic impact. By late 1944, both sides possessed advanced man-portable anti-tank weapons. The Americans had transitioned from viewing the bazooka as adequate to recognizing its limitations against improved German armor. Development of the M20 Super Bazooka began, increasing caliber from 60 mm to 90 mm and penetration from approximately 120 mm to over 250 mm. This weapon wouldn't see service until after the war, but its development reflected the ongoing arms race between armor and anti-armor capabilities. The Germans, meanwhile, continued improving the Panzerschreck and Panzerfaust while simultaneously developing disposable tube weapons that anticipated post-war systems like the Soviet RPG series. The conceptual lineage from the captured American bazooka to modern shoulder-fired anti-tank weapons runs through German engineering efforts from 1943 onward. The British also contributed to this evolution. The projectile infantry anti-tank, or PIT, used a different mechanism, a powerful spring rather than a rocket motor, but achieved similar results. Shaped charge warhead, man-portable, capable of defeating medium tank armor at close range. Every major combatant recognized that infantry needed organic anti-armor capability. The days when tanks could roam battlefields immune to anything except other tanks or dedicated anti-tank guns were ending. The democratization of anti-armor capability was proceeding rapidly, driven by the same industrial and tactical imperatives that created machine guns, barbed wire, and indirect artillery fire. The defensive was reasserting itself against the offensive. The pendulum was swinging. What made the Wehrmacht's response to the captured bazooka significant wasn't merely that. They copied it. Military forces had been copying each other's weapons since the invention of warfare. What made it significant was the speed and scale of the response. From capture in Tunisia in early 1943 to fielding of working Panzerschrecks by October 1943 represented approximately 7 to 8 months. In an era when major weapons programs typically required years from concept to deployment, this timeline was extraordinary. It revealed several factors about late-war German military industry. First, German engineering was flexible and responsive to battlefield requirements when freed from political interference and unrealistic specifications. The Panzerschreck wasn't elegant, it wasn't sophisticated, it was a steel tube with basic sights and an electrical firing mechanism, but it worked. It fulfilled a critical battlefield need. It could be manufactured with available materials and existing industrial capacity. These practical considerations drove development rather than ideological requirements for technological superiority or aesthetic perfection. The result was a weapon that could be produced in quantity and issued to regular infantry rather than specialist units. Second, the timeline revealed the desperate urgency with which German commanders viewed the armor threat. 7 months from concept to fielding meant that normal bureaucratic processes were bypassed or abbreviated. Testing was compressed. Production was prioritized despite competing demands for industrial capacity. Resources were allocated. This urgency reflected awareness that the strategic situation was deteriorating, that German forces would increasingly fight defensive battles against numerically superior Allied armor. That weapons to counter this armor were critical for battlefield survival, rather than merely useful additions to the arsenal. Third, the Panzerschreck program demonstrated that German industry could still produce weapons effectively, even as strategic bombing intensified and resource shortages worsened. Steel tubing was available. Basic electrical components could be manufactured or scavenged. The weapon didn't require precision optics, advanced metallurgy, or rare materials. This simplicity meant production could continue even as Allied bombing destroyed factories and disrupted supply chains. Underground facilities and dispersed workshops could manufacture Panzerschrecks when they couldn't produce tanks or aircraft. The weapon represented appropriate technology for an increasingly constrained industrial economy. The captured bazooka's influence extended beyond the Panzerschreck. German engineers recognized that shaped charge technology could be applied to multiple delivery systems. The Panzerfaust emerged from the same conceptual framework. A disposable tube, simple trigger mechanism, shaped charge warhead. Even simpler than the Panzerschreck because it didn't need to survive multiple firings, cheaper to produce, easier to train soldiers to use. The Volkssturm units mobilized in 1945, consisting of teenagers and old men with minimal training, could be issued Panzerfäuste with reasonable confidence they could employ them effectively. A few minutes of instruction, a demonstration, then hand the weapon to someone who had never fired anything more complex than a rifle and expect them to engage tanks at suicidal ranges. The desperation of late-war German tactical doctrine is evident in this calculus, but the fact that the weapon could be issued to minimally trained personnel demonstrated the success of the design philosophy that began with studying the captured American bazooka. Post-war analysis by American military historians noted the irony that American forces in Europe faced German anti-tank weapons derived from their own bazooka design. The Panzerschreck directly countered American armor using principles and mechanisms that American engineers had developed. This wasn't unique. During the war, both sides regularly captured, copied, and adapted each other's weapons and equipment. The Soviets received American bazookas through Lend-Lease and studied them extensively. British intelligence acquired Panzerschrecks and conducted detailed technical assessments. Japanese forces captured American weapons in the Pacific and attempted to reverse engineer them. The global nature of the conflict and the rapid technological evolution meant that innovations spread quickly across sides. A weapon deployed in Tunisia in early 1943 might appear in modified form on the Eastern Front by year's end. But the Bazooka to Panzerschreck progression was particularly direct. The captured weapon was displayed to German ordnance staff. They immediately grasped its implications. They ordered development of a German version within weeks. They pushed production with maximum urgency. They fielded the weapon in combat within months. The speed of this cycle reflected both German engineering capability and the tactical desperation that characterized Wehrmacht operations from 1943 onward. Every weapon that could contribute to defensive capability was valuable. Every weapon that could be produced quickly and issued widely was prioritized. The Panzerschreck met both criteria. The weapon's limitations were never resolved. The backblast signature remained. The smoke generated by firing revealed positions immediately. The relatively short effective range meant operators needed to get dangerously close to targets. The rocket's slow flight time allowed alert tank crews to take evasive action. The shaped charge penetration was adequate against side and rear armor, but struggled against frontal protection of heavy tanks. Allied tanks with spaced armor or thick frontal plates could usually survive frontal Panzerschreck hits. These limitations meant the Panzerschreck was never a wonder weapon that could reverse German fortunes. It was simply a tool that made German defensive positions somewhat more capable of resisting Allied armored attacks. The human cost of operating Panzerschrecks was substantial. Rocket teams had to position themselves within 100 to 150 meters of enemy tanks, had to expose themselves to fire the weapon, had to relocate immediately after firing to avoid retaliatory fire. Many operators were killed during or immediately after engagements. Tank machine guns, infantry small arms, artillery, and air attacks all threatened Panzerschreck teams. The weapon gave infantry the capability to fight tanks, but fighting tanks remained extremely dangerous. Veterans' accounts describe the psychological stress of waiting in a foxhole or behind a wall while a 50-ton tank approached. The calculation of when to fire. Too early, and you might miss. Too late, and the tank might see you first. And after firing, regardless of whether you hit or missed, every enemy weapon in range would target your position. The courage or desperation required to operate Panzerschrecks in combat shouldn't be underestimated. These were often teenagers or undertrained men thrust into situations requiring them to engage armored vehicles at ranges where they could see the crew through the vision ports. Finnish forces provided interesting comparative data on Panzerschreck effectiveness. Finland received approximately 1,854 launchers and 18,650 rockets from Germany before signing armistice with the Soviet Union in September 1944. Finnish troops used Panzerschrecks extensively during the final phase of the continuation war against Soviet forces. Post-war Finnish military analysis indicated that the weapon performed adequately against Soviet 34 and KV tanks when engaging from favorable positions at appropriate ranges. But Finnish crews also noted the difficulties. The weapon was heavy for extended infantry operations. The backblast limited where it could be fired. The rockets were bulky and difficult to carry in quantity. A two-man team could carry perhaps 6 to 8 rockets in addition to their other equipment. After expending their ammunition, they were effectively disarmed unless resupply was available. In fluid combat situations, resupply was rarely certain. Finnish combat reports suggest that Panzerschreck teams typically engaged once or twice per action before withdrawing or transitioning to other weapons. The weapon provided burst capability rather than sustained anti-armor fire. The Finns continued using Panzerschrecks through the 1950s, long after the war ended. This longevity reflected both the weapon's utility and Finland's limited military budget. The rockets and launchers Germany had provided were high quality and properly stored. Ammunition remained serviceable for years. The weapon filled a gap in Finnish anti-armor capability at minimal cost. Only when more modern systems became available did Finland finally retire the Panzerschreck. The fact that a weapon hastily developed in 1943 remained in military service over a decade later speaks to the fundamental soundness of the design for its intended role. The Soviet Union took particular interest in German anti-tank rocket launchers. After the war, Soviet engineers examined captured Panzerschrecks and Panzerfäuste extensively. The RPG-2, introduced in 1949, showed clear influence from German designs. Later, Soviet rocket-propelled grenade systems continued this lineage. The RPG-7, perhaps the most successful man-portable anti-tank weapon ever designed, reflected lessons learned from studying German, American, and British rocket launchers. The shaped charge warhead, the man-portable launcher, the balance between penetration and portability. These design elements traced back to the weapons developed during World War II, including the Panzerschreck that Wehrmacht engineers created after examining a captured American bazooka. American post-war development followed similar trajectories. The 3.5-inch M20 Super Bazooka entered production shortly after the war ended. Testing in Korea against Soviet-supplied 34 tanks validated the concept. Later, American designs incorporated lessons from German weapons while advancing the technology. The M72 light anti-armor weapon, disposable and compact, reflected principles first demonstrated by the Panzerfaust. The evolution of anti-armor weapons continued through the Cold War and into the modern era, but the conceptual framework remained consistent. Infantry needed man-portable weapons capable of defeating armored vehicles. The technology to enable this had emerged during World War II through rapid innovation driven by battlefield necessity. The story of Wehrmacht engineers testing a captured bazooka in November 1942 and immediately understanding its implications represents a moment when tactical reality overrode technological conservatism. German military tradition emphasized heavy weapons, precision engineering, and complex systems operated by specialists. The bazooka represented the opposite philosophy: simple mechanism, mass production, issue to regular infantry. The fact that Wehrmacht ordnance staff immediately pushed for German development of a similar weapon revealed awareness that traditional approaches weren't sufficient for the defensive battles ahead. That numerical inferiority required force multipliers, that infantry needed organic anti-armor capability because dedicated anti-tank guns couldn't be everywhere simultaneously. The democratization of anti-armor capability that began with shoulder-fired rockets had profound implications beyond World War II. Modern conflicts feature sophisticated man-portable anti-tank weapons descended directly from wartime developments. Javelin missiles, NLAW systems, RPG variants, all trace conceptual lineage to the realization that infantry with proper weapons could threaten armored vehicles. This realization emerged during World War II, when engineers on multiple sides recognized that shaped charge technology, combined with rocket propulsion, created possibilities that hadn't existed previously. The Wehrmacht's rapid development of the Panzerschreck after capturing American bazookas was part of this broader technological evolution. What's striking from historical perspective is how quickly battlefield innovations propagated during the war. Technologies that might have taken decades to spread in peacetime moved from one side to another in months. Captured weapons were immediately analyzed. Successful designs were copied or adapted. Production began with minimal delay. The compressed timeline reflected the existential nature of the conflict. Innovations that provided battlefield advantage couldn't wait for peacetime development schedules. They needed to reach troops as quickly as possible. This urgency drove engineering efforts and streamlined bureaucratic processes in ways that peacetime military establishments found difficult to replicate. The specific technical details of the Panzerschreck's development reveal the engineering challenges and solutions. The 88mm rocket motor needed careful balancing of propellant quantity, burn rate, and structural strength. Too little propellant meant insufficient velocity and reduced penetration. Too much propellant meant excessive backblast and potentially dangerous pressure levels in the launch tube. The shaped charge warhead required precise geometry. The copper liner's thickness and angle determined how effectively the explosive force would be focused into a penetrating jet. The standoff distance between the warhead and the target affected penetration. Too close and the jet didn't form properly. Too far and the jet dispersed before penetration. These technical challenges were resolved through iterative testing using resources that were increasingly scarce as the war progressed. The electrical firing mechanism presented particular problems. Early Panzerschrecks used systems similar to the American bazooka, with battery power. German engineers quickly discovered that batteries failed in cold Eastern Front conditions. The solution was a magneto system. Pulling the trigger compressed a spring that drove a small generator, creating the electrical impulse to ignite the rocket motor. This system was more reliable across temperature ranges and didn't require battery replacement. It also eliminated concerns about batteries losing charge during storage. The magneto-firing mechanism became standard on later Bazooka variants as well, demonstrating how improvements made by one side eventually influenced designs on the other side. Sighting systems remained crude throughout the war. Both bazookas and Panzerschrecks used simple iron sights or basic optical sights. Sophisticated fire control systems weren't practical for weapons that needed to be cheap, rugged, and simple enough for minimally trained infantry to operate. The consequence was that effective engagement range remained limited. Even skilled operators struggled to hit targets beyond 150 meters. The slow rocket velocity meant that moving targets were difficult to engage. The operator had to lead the target, accounting for both the target's motion and the rocket's flight time. Under combat stress, with incomplete training, many shots missed entirely. Statistical analysis suggests that tactical effectiveness depended more on positioning and tactical employment than on raw hit probability. Ambushes from prepared positions at close range were far more successful than hasty engagements at longer distances. Urban warfare provided ideal conditions for Panzerschreck employment. Buildings channeled armor along predictable routes. Sightlines were short. Engagement ranges fell within the weapon's effective envelope. Upper story positions allowed downward shots against thinner top armor. Multiple positions could provide overlapping fields of fire. Allied forces learned to fear German anti-tank teams in cities. Extensive preparatory artillery fire became standard before committing armor to urban combat. Infantry would systematically clear buildings before tanks would advance. The process was slow, costly, and necessary. Multiple documented incidents describe individual Panzerschreck teams temporarily halting company or battalion-sized armored units by destroying lead vehicles in narrow streets, creating obstacles that took hours to bypass or clear. The psychological dimension of Panzerschreck employment shouldn't be overlooked. Allied tank crews knew that any position might conceal anti-tank rockets. This knowledge created persistent low-level stress that degraded crew performance over time. Constant vigilance, reluctance to close with infantry positions, preference for indirect fire or calling for infantry support rather than engaging directly. These behaviors were tactically sound, but they slowed operations and reduced the tempo of Allied advances. German forces gained time. Hours became days. Days became weeks. The cumulative effect was that Allied offensives took longer and cost more than they might have if German infantry lacked effective anti-armor weapons. German defensive doctrine evolved to incorporate Panzerschrecks systematically. Infantry units established defensive positions with interlocking fields of fire. Anti-tank teams were positioned to cover likely armor approaches. Alternate positions were prepared for movement after firing. Artillery concentrations were pre-registered to cover withdrawal routes. The doctrine emphasized that Panzerschreck teams weren't expected to stop armored attacks alone. They were one element of integrated defensive systems combining obstacles, mines, anti-tank guns, artillery, and infantry weapons. But they were a critical element because they extended the defensive depth. Allied armor couldn't simply bypass prepared anti-tank gun positions. They had to account for rocket teams dispersed throughout the defensive zone. This made offensive operations more complex and time-consuming. The industrial achievement of producing over 300,000 Panzerschrecks during the war deserves recognition. German industry in 1943 through 1945 operated under severe constraints. Allied strategic bombing systematically destroyed factories, rail infrastructure, and electrical generation. Raw material shortages forced substitution of inferior materials in many weapon systems. Labor shortages meant increased use of forced labor with predictable quality control problems. Despite these constraints, Panzerschreck production continued until the final weeks of the war. This reflected both the weapon's relative simplicity and the priority placed on anti-armor capability. When resources had to be allocated between competing weapons programs, the Panzerschreck received sufficient priority to maintain production. This decision reflected tactical assessment that German forces would fight primarily defensive battles, where infantry anti-armor weapons were essential for survival. The weapon's legacy extends beyond its immediate tactical impact. The concept that infantry should possess organic anti-armor capability became accepted military doctrine worldwide. Modern mechanized infantry units universally include anti-armor weapons at squad and platoon levels. The specific technologies have evolved: wire-guided missiles, laser designators, top-attack munitions, fire and forget guidance, but the underlying principle remains unchanged. Infantry must be able to defend themselves against armored vehicles without requiring dedicated anti-armor specialists or heavy weapons. This doctrinal consensus emerged directly from World War II, experiences with bazookas, Panzerschrecks, and similar weapons that demonstrated ordinary infantry could destroy tanks with appropriate equipment. The human stories behind the statistics deserve remembrance. Young soldiers on both sides carried these weapons into combat. Many never returned. Tank crews burned alive when shaped charge jets penetrated ammunition storage. Rocket operators torn apart by machine gun fire after revealing their positions. The tactical calculus often came down to who died, not whether someone died. Close-range anti-tank combat was mutual slaughter, where victory meant survival rather than glory. Veteran accounts describe the desperate courage required to hold position while a tank approached, the split-second decision of when to fire, the knowledge that missing likely meant death, the psychological aftermath of successfully destroying a vehicle and knowing the crew inside burned or suffocated. These human dimensions transcended national boundaries. Fear, courage, trauma were universal regardless of which side someone fought for. The captured American bazooka that Wehrmacht engineers examined in November 1942 was a mass-produced weapon, one of many thousands manufactured. The engineers who studied it were professionals performing assigned duties. The soldiers who would eventually operate the Panzerschreck derived from that study were conscripts, volunteers, and Volkssturm mobilized by desperation. None of them could have foreseen that the technologies they employed would influence military doctrine for the next 80 years. They were focused on immediate tactical problems. Surviving the current battle, holding the current position, getting through the current day. The broader strategic and historical implications were invisible to them. Only in retrospect can we trace the connections between a steel tube captured in Tunisia and the evolution of modern anti-armor warfare. The irony that American infantry faced German rockets derived from American rocket design wasn't lost on contemporary observers. General George Patton, commanding Third Army in France, noted in May 1944 correspondence that the bazooka's purpose should be defensive rather than offensive, that infantry shouldn't hunt tanks but should use rockets as last resort weapons to prevent being overrun. This assessment reflected recognition that close-range anti-tank combat favored the defender. The side that could choose positions, prepare ambushes, and engage at moment of maximum advantage held significant tactical benefit. German forces, fighting primarily defensive battles from mid-1943 onward, could employ Panzerschrecks from prepared positions. Allied forces, conducting offensive operations, had to advance through terrain that might conceal rocket teams in any position. The asymmetry favored defenders, which partially explains why German forces could conduct effective defensive operations despite overall strategic deterioration. By April 1945, with Germany facing collapse, Panzerschreck teams were among the last organized resistance in many areas. Volkssturm units with minimal training were issued weapons and told to defend their cities. Scattered Wehrmacht remnants fought rearguard actions to cover withdrawals. Waffen-SS units continued resistance past any rational hope of success. In all these final battles, Panzerschrecks appeared not because they could change outcomes, but because they were available and infantry needed some capability against Soviet or Allied armor rolling through collapsing German defenses. The weapon that had been developed as a force multiplier to extend German defensive capability became a symbol of hopeless last stands. Young boys and old men with rockets facing mechanized armies, the desperation was complete. The post-war disposition of captured Panzerschrecks reveals interesting details. Allied forces collected thousands from German surrenders and battlefield captures. Intelligence units conducted extensive technical analysis. Testing occurred at American, British, and Soviet facilities. The weapons were dissected, measured, and evaluated. Test firings occurred to validate performance claims. Allied engineers confirmed that Panzerschreck penetration exceeded bazooka penetration significantly. The 88mm shaped charge outperformed the 60mm charge by substantial margins. This data informed post-war anti-armor weapon development. The M20 Super Bazooka incorporated lessons from both American wartime experience and analysis of German weapons. Soviet designs similarly reflected study of captured equipment. The technology transfer wasn't espionage or secret intelligence. It was simple examination of captured weapons and incorporation of successful design elements into future systems. Some captured Panzerschrecks saw post-war service with Allied-aligned forces. Chinese nationalist forces received some during the Chinese Civil War. Various European nations used captured stocks until domestic production or foreign purchases replaced them. The weapons remained serviceable for years if properly stored. The rockets degraded over time, but slowly. Several nations maintained captured Panzerschrecks as training aids or museum pieces. Some still exist in military and civilian collections today. 70 years after their manufacture, they stand as physical evidence of the rapid technological innovation that characterized World War II. Each surviving example represents the work of engineers, factory workers, and soldiers whose individual contributions combined to create military history. The question remains whether the Panzerschreck achieved its intended strategic effect. Did it enable German forces to resist Allied offensives more effectively than they could have without it? The answer is almost certainly yes, though quantifying the impact is difficult. German defensive operations from 1943 to 1945 were more effective than Allied planners anticipated. Multiple offensives stalled or required significantly more time than projected. Casualty rates for Allied armor remained substantial throughout the European campaign. German infantry demonstrated persistent ability to conduct effective anti-tank defense even when outnumbered and outgunned. The Panzerschreck contributed to these outcomes. It wasn't the only factor. German tactical doctrine, training, defensive preparation, and willingness to accept casualties all mattered, but the availability of man-portable anti-armor weapons definitely made German defensive positions more dangerous and costly to reduce. Conversely, the Panzerschreck couldn't prevent Allied victory. No weapon system could have changed the fundamental strategic balance by 1943. German industrial capacity couldn't match combined Allied production. German manpower couldn't replace losses at rates comparable to Allied reinforcement. German tactical success in defensive battles won time, but couldn't alter final outcomes. The Panzerschreck made German forces more tactically effective, while the strategic situation continued deteriorating. This dynamic characterized late-war German military operations generally. Excellent tactics executed by well-trained soldiers using effective weapons couldn't compensate for strategic-level deficiencies. The Wehrmacht could delay defeat. It couldn't prevent it. The story of Wehrmacht engineers testing a captured bazooka and rapidly developing the Panzerschreck illustrates several themes that defined World War II. The rapid pace of technological innovation, the mutual influence of weapons development across sides, the relationship between tactical tools and strategic outcomes, the human cost of technological advancement in warfare, the persistence of fundamental military problems despite technological solutions. These themes resonate beyond historical interest. They remain relevant to contemporary military affairs, where technological change continues accelerating, where adversaries continue studying and copying each other's innovations, and where tactical success doesn't guarantee strategic victory. For the engineers examining that captured bazooka in November 1942, none of these grand historical themes were visible. They saw a weapon with potential. They recognized problems that needed solving. They understood urgency. They proceeded with development. Their work contributed to one of the more successful German weapons programs of the late war period. The Panzerschreck wasn't a war-winning weapon. No single weapon could have been. But it was an effective tool that served its intended purpose of enhancing infantry anti-armor capability. In the desperate defensive battles of 1944 and 1945, that capability mattered to the soldiers who carried the weapons and the Allied tankers who faced them. The democratization of anti-tank capability that began with simple shoulder-fired rockets during World War II continues into the present era. Modern conflicts feature infantry with weapons capable of destroying the most advanced armored vehicles. The balance between armor and anti-armor continuously evolves through technological advancement. Active protection systems, reactive armor, composite materials, top-attack munitions, tandem warheads. The contest continues. But the fundamental principle established during World War II remains valid. Infantry with appropriate weapons can threaten armored vehicles. The teenager with a tube can kill the tank. That realization, which Wehrmacht engineers grasped when testing a captured American bazooka in November 1942, and fundamentally altered infantry armor dynamics for the remainder of the 20th century and beyond. Thank you for watching. For more detailed historical breakdowns, Check out the other videos on your screen now and don't forget to subscribe.